So, we'll still trying to set things up. Welcome, everyone. So today is a little bit special for a couple of reasons. If you're joining for the first time or watching us on...
We're not live yet.
We're not yet live yet. That's totally fine.
We hear you guys.
Perfect. I have to get the mic is there. Anyway, so if you're joining us for the first time on YouTube or a streaming link, welcome. This is Random Samples. It's a weekly seminar series where we invite internal and external guests to come talk about the latest and greatest in AI. If I can make one request, if you've shared any of these things before, you do not need to worry about, you don't need to DM me. The talks that had a public tag in them, they are totally fine to share. Okay, with that, I want to welcome Mark Kurtz today, our resident expert and all things LLM compression. Mark is going to take us on a journey to show how technologies that emerge in research on model compression get into production. So Mark, without any further ado, I'll let you take over the screen.
Awesome. Thanks, Akash. Sorry, one sec. My computer is not being. All right, I think it's working now. Let me see if I can share. All right, there we go. Hopefully that is working. Can everybody see it okay?
It looks good, Mark.
Okay, thank you. All right, so thanks, Akash, for introducing me. Sorry about those quick technical issues. My name is Mark Kurtz. I'm going to be running through State of LLM Compression from research to production. So we'll discuss today. In general, we'll go through just a high level on the landscape, and then dive into how compression is really starting to help some of the issues that are coming up in the landscape, and why compression is pretty much becoming a non-optional if you're going into production, but also framing the gaps that are starting to develop between research and production. And then we'll start doing a deep dive into the various techniques, and then we'll wrap up with a conclusion. If anybody has any questions along the way, definitely feel free to ask. Akash, if you see anything come up in the chat, because I cannot see it on my screen right now, definitely interrupt me, and I'm more than happy to dive in.
Absolutely.
All right, so let's dive into the landscape. Here is just a quick primer on LLMs and on what happened, right? When ChatGPT came out, really started transforming where the investments in both the AI research side as well as AI enterprise projects and investments went. And these articles were essentially everywhere. And this was reflected at all levels, as I said, from research as well as into boards at various enterprises. So the first thing is that LLMs are everywhere. They're dominating the AI research enterprise investments, as I said, and particularly for content generation, code generation, RAG, and summarization. So overall, they're working very well towards augmenting human work. Active prototypes are increasingly moving to production. Currently, estimates are around 3 to 10% of prototypes are making it into production. Generally, those are more on the internal side for enterprises, but projections are roughly around 30% starting to move in within the next year or two. The other piece, though, is as we're moving these prototypes into production, inference spending is continuing to scale to serve them. So overall estimates right now are around 106 billion for this year, all just going straight to inference, no training at all. And then roughly 255 billion by 2030. And let's dive into, models. Models won't stop growing. So this is a pretty popular image from the scaling loss paper, right? Just showing as we increase model size, then we're going to be able to increase our accuracy and, as shown in this, decrease our loss. There is a diminishing returns as shown here, but yeah, let's dive in. So models began to scale very quickly. Early on in 2023, models were increasing in size, as I said, very quickly, from millions of parameters to hundreds of billions. Llama 3 was roughly an inflection point where 405B kind of maxed out most of the open source models, and even the closed source models are generally smaller than these, and made up of multiple different experts and things like that. And this was due to diminishing returns as the model sizes scaled. Mixture of experts have restarted this growth. And what I mean by mixture of experts is that they are enabling more parameters overall, but we're only going to use a few of those parameters on any given forward pass and inference. So that's what we mean by active. So with the latest Llama 4 release, what we see is this trend now starting to kick off again. 109 billion and 400 billion parameter models coming out, and then a Llama 4 behemoth, which is still training, 2 trillion parameters. And then let's look at where we're at on the hardware side. And GPUs are particularly stuck in memory. So we're looking at a GPU evolution, going from V100, 32 gigs up to A100 and H100 at 80 gigs, and now the B200 is finally getting up to about 192 gigs. But how does this compare overall? Oh, sorry, this next slide. But yeah, and along these lines, GPUs are also expensive. 40K per H100 right now. It's roughly where the expectation for B200s is being set. And then we have manufacturing and usage limits that are really driving this expense. It's primarily due to HBM memory. It's hard to scale due to manufacturing. There are a lot of defects as you get to those sizes, and it's really hard to guarantee that that you'll be able to reach that that general size. Cerebrus and others are kind of on the extreme end of what they can do with memory, but they have a lot of stuff that they have to do on the manufacturing side to make that happen, and also a lot of redundancies built into the chips. Also, memory to compute ratio, from V100 up to B200 has roughly been the same. And this is primarily because whenever they're developing these chips, they're optimizing for how they're going to be used. Early on, they were for graphics. Now, primarily looking at AI inference and training. And AI inference and training have different loads, where training is very, very heavy on compute. Inference is much less so. So to be able to answer all of this and these limits that are happening on HBM, we're scaling with interconnects now. So infrastructure is actually being designed and installed as interconnect first, where we're looking at NVLinks, NV switches, all kinds of stuff like that, with extremely fast GPU to GPU communication over some type of network. And this is just increasing cost and complexity even further. So let's look into what that cost actually is. So just for fitting parameters, 109 billion model, it's about 218 gigabytes. That's 3 80 gig GPUs. 400 billion model, that's 800 gigs. That's 10 80 gig GPUs. And then trying to fit, that was just parameters fitting the auto-regressive request, including the KV cache. Usually it's around 2.5 megabytes per token across the KV cache. Then we end up with 2.5 gigabytes for medium context requests to add on to our parameters, and 25 gigs for a long context. Medium here being about 1,000 tokens, and 25 being 10,000 tokens. Then scaling out to users for these enterprises, right? 15 to 20 parallel users for 109 billion parameter model on an 8 by 80 gig GPU. That's roughly what we're going to be able to max out at that longer context. Same thing happens for the 400 billion whenever we're on, this time, 2 by 8 by 80 gig servers. And ultimately, that means a lot of costs. So to run those servers, just the 8x80 gig, usually we're looking at somewhere around 30 to 60K a month. There definitely are ways to reduce that cost, either by purchasing or by reserving, things like that. But this means that for enterprise level deployments, where you definitely have more than 15 users coming in at a time, we're looking at hundreds of thousands of dollars to deploy one of these models per month. And then smaller orgs are usually in the tens of thousands. So let's talk over how compression helps out. And let's look at the two main bottlenecks for inference costs. It's the required memory footprint / bandwidth per request, and then the compute required per request. So obviously we can fix both of those by shrinking that model size. And overall that can hurt accuracy. Smaller models are definitely cheaper, but fairly expensive. And we're reducing our potential accuracy, though that may be acceptable, right? Because we can train a smaller model on the compute that we have available. So therefore we can actually converge something that's specialized to our data set. Excuse me. But compression is a smarter orthogonal way that can actually apply across both of these pathways. And looking at it, deep learning models are over-parameterized with many redundancies. So what was important during training goes unused in inference. This works for all model sizes and inference scenarios. At least it's been tested so far. And then looking at research compression paths. So there's generally two paths that happen in the research compression community, where one is that we're focused on preserving original accuracy and the papers are going out highly focused on that. So given that, we're going to maximize compression as long as we can get to 99% of the original accuracy or something along those lines. The other side is where academia will define what usable accuracy is and therefore maximize compression to it. So essentially, if the model didn't fall apart and it can still answer, then we're going to try and maximize that compression. And that's much more used on the academic side, whereas the former is essentially all that makes it to production. Sorry, and then one other point on this is just that one of the reasons why we're looking at production for those is primarily because if we're not meeting that original accuracy, then we get into questions of, well, what does that look like if I just use a smaller model and maybe train it for longer, things like that. So real quick, so that we can talk through how compression affects and different compression methods and types can affect the transformer architecture in the LLMs. Let's look at just a quick review on this. So we have core building blocks, right, where we have weights. These are the weights going into both our positional embedding as well as our classification head, but also our intermediate fully connected layers and the QKV layers that are going into attention. We have our activations, which are the intermediates in between these layers. We have KV cache, which is broken out separately because this is a remnant of autoregressive inference where we want to keep the past state that we've generated around so we don't have to recompute that state. So KV cache being kept separate for pretty much all of these compression methods. And then we have attention dynamic token to token interaction, right? So within attention, just being able to define a very large matrix multiply and a series of matrix multiplies to be able to generate those token interactions. So compression technique targets. The techniques may target just one building block, or multiple, or all of them. And then some common groupings for compression is what I call type 1, type 2, and type 3. These are not ordered by preference or anything, other than type 1 is generally the most common. And also, what we're going to go into is a non-exhaustive list. These are just the most popular that I've generally been made aware of and have deeper understanding of, I should say. So let's talk to type 1, where we're going to reduce the model. So the goal is to keep or reduce the model dimensionality, enabling lower memory footprint / bandwidth and or compute. So these include things like quantization, where we're reducing the precision of weights, activations, KV cache, and or attention, lower memory requirements, and less compute with hardware compatibility. We have pruning and sparsity. where we're removing redundant weights or activations by setting them to 0. This can be flavored in unstructured, semi-structured, which we'll go through later. And then additionally, we have structured pruning or low-rank decomposition. These are where we're removing sections from the model entirely in the structured pruning case, which we'll go through a little bit more later. And in the low-rank decomposition case, we're replacing linear layers with multiple smaller matrices to try and emulate that larger, more expensive matrix. And then finally, we have weight sharing. So this is where we're going to utilize the same parameters for multiple layers. There is another thing that could arguably be in here, which is the talk that was given last time, which is model merging, but where you can take multiple models and fold them together to ultimately get better accuracy. Essentially kind of works into that mixture of experts that we were talking over, or just kind of a general experts setup. So let's talk through type 2, which is extending the model. So our goal is to add to the model dimensionality while reducing requirements for running the overall model. The main and really the only important method under here is speculative decoding. So this is where we're going to take a small speculator model, or we're going to add extended layers on top of the original model, where that smaller model is predicting multiple tokens ahead, and the larger model is going to verify whether those smaller model tokens are correct. So provided our request rate is lower and our compute therefore isn't saturated on the GPUs, this is going to overall provide faster requests and faster latency. If we're saturated on compute, then essentially we're just wasting compute on the on running the smaller model, because we could have just ran that larger model with the same amount of compute, since we do have to run that larger model anyways over all tokens to validate them that they are correct. And then type 3 is teaching a smaller model. So we're going to utilize a larger model to transfer or extend a smaller model's capabilities, enabling reduced requirements and higher accuracy. So we have knowledge distillation under this. Edit the loss function while training a smaller model so that it must match the distributions from the larger model. Enables more signal than what is available through the next token prediction. And then we have data distillation, which is where we generate a synthetic enriched training data set, enabling higher quality data along with data expansion, especially for targeted use cases where we may not have that much data. So let's talk through and deep dive into type 1, reducing the model. Let's go through quantization one more time. I will say quantization and sparsity are definitely much heavier in terms of the content, and the others are a little bit lighter. So quantization review. We're reducing the precision of our targeted portions of the network from generally 16 bits, sometimes 32-bit, but for the most part 16-bit now, down to 8-bit integer, 4-bit integer, 8-bit float, 4-bit float, or lower. And I'll go through the usages of these in a second. But overall, looking at this image, we have our original distribution represented here at the top, and in a very large representative space, and we're going to project that into a much smaller space. And you can see how we're just trying to fit what bins in that smaller space, because we have limited precision. Each of those values should go into, so that we can best preserve our accuracy. So quantization overall is reducing the information in the model, as I said, projecting from a larger domain to a smaller. So ultimately, we're balancing the trade-off of how much information we actually need to preserve in that model. In general, training has very noisy updates, so the reduction is generally removing those redundancies that we built in during training. And then diving back into when to use 8-bit, 4-bit, things like that. Hardware support varies across accelerators and CPUs. If we're just doing memory lookups, then pretty much any format works. But the notable piece is that memory lookups really only help in the latency case, right? Where we have a limited number of streams or single stream, things like that. That's why you see, things like GGUF in a lot of popular formats, which I'm not going to go into here, primarily because there's not a lot of published research on those or really even evals on those. But they are a really fun community project where we're doing all kinds of weird formats because you're running those locally, and your execution time is completely dominated by loading the weights into memory so you can execute them. But otherwise, 8-bit int is fully supported on Ampere and earlier generations. So generally, if we're deploying on Ampere or CPUs or TPUs, then we're looking at an 8-bit format. 4-bit is there's limited support for that, at least for compute speed up, so not a ton across accelerators. But then we get into 8-bit float, which is in the Hopper generation for NVIDIA, and I believe the newer Ampere generation, or AMD generations. And then 4-bit float is coming out with the Blackwell series from NVIDIA. So let's run through the state of quantization. And first, let's start off with some notable research developments. First is to note, standard round to nearest didn't work well for LLMs. This is where we're just doing exactly what I illustrated on that previous page, given that outlier distribution, or that input distribution, round it so that it fits into the smaller distribution. And this was primarily because there are a lot of outliers, both mainly in the, actually in both weights and activations. GPTQ came out in 2023 with actually a principal research scientist now at Red Hat, Dan Alisar. So this was the first to work well and enabled 4-bit weights through second order updates. So essentially what we're doing is defining each layer that we're trying to quantize as a separate problem. And then given that we are iteratively quantizing that model, we can figure out how to update the remaining weights. So we can essentially accumulate error and update for error as we roll in. There were some other fixes here to make the general rounding schemes and things like that work much better, especially with the outliers, but that was the main case there. Smooth Quant should say 2023. But additionally, that's Smooth Quant. So this was enabling 8-bit weights and activations through channel-wise smoothing. So what they noticed is that activations were a lot harder to quantize because they had a lot more outliers. But what we could do is essentially add a scale and fold that scale into the weights so that we could normalize the distributions of the activations a lot more by pushing that incorrect distribution, or that what's the word I'm looking for, focus distribution into the weights, because the weights essentially could afford it. We have QLoRa that came out after that. This was first to introduce the concept along the lines of codebooks. And what I mean by codebooks is that rather than taking an int4 representation where we're doing 0, 1, 2, 3, 4, 5, and so on, we can actually shift the meaning of the underlying each data type. So we could say 0 actually maps to a much larger portion of the distribution that we're trying to quantize. So this becomes particularly important. Actually, let me go back just real fast. This becomes particularly important because usually the higher magnitudes are the ones that carry more information, and the ones around 0 are much more common, but they don't really carry a lot of information. So we want to push the bands of information out to these larger values so that we can preserve more meaning and more information through those. Next, we had Quip, and Carrot is not Qualrat. I've been yelled at for pronouncing it like that from the author, but Quip and Carrot. These introduced and expanded upon this idea of incoherence processing. So what was noted within these models was that the activations and the weights and things like that, typically you only had a few channels that had severe outliers in them, and those were extremely hard to quantize. So rather than doing something like Smooth Quant or AWQ, which is coming up next and I'll explain, what this is doing is adding in a Hadamard rotation, which is essentially it's a predetermined multiplication of negative ones and ones that are orthogonal to each other, but it comes out to be a random multiplication. So those channels that were large outliers, the information contained in those are spread out across the entire rest of the matrix. Well, it'd be across the rows, but you spread out that information so that now you have a much more Gaussian distribution that you're trying to represent. And again, going back to that earlier distribution, this is ultimately what we want to get to is a Gaussian distribution for everything, and that's what this incoherence processing allows. So we can spread that out.
Hey, Mark. A couple of questions from YouTube. I'm gonna read them one by one. If you're gonna cover it and later, feel free to defer it.
That's good.
Take them right now. That'd be great. So the first one is, I think proposed compression technique will contribute to more loss as we will lose information. How we can control it as we scale? And the question specifically is, are you applying some normalization layers in between?
No normalization layers, but I'll go through a little bit on the accuracy impacts in the next slide, as well as in various slides after. But the notable thing here is that, again, there are ways that we can preserve accuracy. All of these algorithms coming out here are ways so that we can preserve accuracy, even though we are removing information, because they're removing targeted noise in the network rather than actual information needed to make essentially filtering and decisions within the network. But we'll go through that a little bit more on the accuracy impact. Next slide.
Awesome. So I think this one also be probably tackled then, but I'll just read it out right now. So the second question is, how big of a role does calibration have? I think LLM compressor can use a calibration data set, but examples by default don't use it.
Yeah, that's a good question, and I didn't dive into that much detail here because we don't have too much time. But just quickly on that, it depends on the method that you're going for. So a lot of the examples that are in LLM compressor, which is our compression toolkit that implements a lot of these algorithms, that is a lot of those examples are illustrating an FP8 pathway, and actually what it's doing is targeting the weights at FP8. Because the weights are already trained and a static distribution, we know exactly that distribution, so we don't need any active data coming through to better essentially adjust that information, unless we're doing something like GPTQ or others. And also, they're combined with something called dynamic per token quantization. So on the activations, we're actually quantizing those on the fly by generating a distribution on statistical distribution on the fly to quantize down to it. These are techniques that you can get away with at higher precisions. So whenever we're at FP8 especially, that's a lot easier because FP8 has a much closer match to FP16 in terms of the overall distribution. So you're not losing a ton of information. You can get away with essentially doing data free without having to update the rest of the network. As we get into Ent8, which does have a different distribution, which isn't right, it is much more even in the buckets that it generates, or lower precision. That's where we hit issues and we need these more advanced techniques. And with that, we need either calibration data or training data.
Awesome. I think there was a comment about the new 1-bit model from Microsoft, but I think I'm going to leave that probably to the end if you want to make a comment about that.
Yeah, that sounds good. All right. So as I said, with AWQ came out in 2024, and it enabled a simpler method to get to 4-bit in comparison to GPTQ, which is doing a fairly heavy weight update. Usually AWQ and GPTQ are compared to each other quite a bit. Which one works kind of depends on what you're doing and how much you tune it. GPTQ usually comes out a little bit better though. But AWQ is much simpler to implement because what they realize is that there are a number of salient weights that actually matter for the rest of the network coming after it. So what you can do is scale those salient weights so that you can better represent them in the distribution. And you determine that essentially by the channels times the magnitudes, which this is a pretty common theme of the activations times the weights, the magnitude of those, and it's a pretty common theme across compression techniques. That's primarily just because once we have the activations times the weights, the largest value there is the one that's going to dominate the output from the layer. We then get into Quip Sharp, which is a combined incoherence processing. It combined the incoherence processing, the head-of-mark rotations that we talked through, along with efficient code books. So what they did is actually figured out, given that we have applied incoherence processing to the model, we know that that distribution is going to be Gaussian now because we're applying that random rotation. And what we can do is optimize a code book to best represent a Gaussian distribution. And because we have the information spread out and randomized across the network, we no longer have these outliers and things like that that we do want to focus on in the quantization setup. So these efficient code books essentially can be pre-computed. And again, now we're going back to, we're not representing equivalent buckets in our downsampled space, but we're going to assign varied size buckets so that we can group more of the weights, more of the values in the upstream distribution together, and therefore be able to focus more of that distribution on important values. And then they also finally did some fine tuning on top of that, quantization aware training, where they're just fine tuning the values so that so they can get the model to converge a little bit better. And then SpinQuant, this introduced learned rotation matrices. So rather than taking that pre-computed Hadamard matrix, it was actually going through and flipping which one was -1 and 1 through a fairly complex algorithm, so that you could optimize essentially the distribution of information across the network. Again, kind of trying to target those larger values and make sure that those are spread out more and therefore represented more in our quantized distribution. And then finally, we have some newer techniques which are really highly focused on the KV cache, Aqua KV and Squat. Squat we went through, I think that was 2 weeks ago, which is a great presentation. Aqua KV is another technique along these lines, but both of these are doing some type of either projection or targeted optimization specifically for the KV cache, because the KV cache is a little bit different from the rest of these. In the case of Aqua KV, they figured out that you can actually apply a learned linear projection to figure out what the next tokens are, and you can use that to better approximate the quantization. And then Squat was doing a optimization specifically for how the KV cache interacts with each other, so you can better represent the information inside of that. But all of these techniques really highlighted, and the reason why I called these out is that they really highlighted that high recovery at 4-bit to the 99% level, or lower precision a little bit less. I will say Aqua KV and Squat, those can get to lesser precision because they're targeting that specific KV cache rather than the rest of the network.
Mark, there's a question from William.
Yeah.
Can the various techniques be combined together, or is it one or the other?
Yeah, that's a great question. There's some quite a bit of research going out towards that. There's something called GPTQ v2 that just came out. That was combining GPTQ plus incoherence processing and some updates on top of GPTQ. So there's definitely ways to combine these, and this is where a lot of the newer research is going, is just combinations of these foundational pieces. All right, great. So let's look at the current research state, which I alluded to a little bit, but 2 to 3-bit for maximal compression with a reasonable model on the academic side. So this is going to differ based on what you target, as I said, but generally 2 to 3-bit, you can get a reasonable model out. This is not full recovery. 4-bit is fairly safe though for full accuracy recovery. It does differ again based on targets, but there are some really promising methods that are getting close to full recovery for the entire network at 4-bit. Otherwise, if you leave some of the parts out, or go to higher precision for some of the parts, you can generally get close to that 4-bit level. So for production state, 4-bit weight only works at scale. And generally, you want to do this for latency sensitive use cases. This is usually about a 1.5 to 3x speed up. And then 8-bit for weights, activations, KV cache, and attention all work at scale, which is again around a 1.5 to 3x speed up. Depends on a lot of factors, but this is generally what works. What's interesting is that for the attention side, actually Flash Attention v3 is architected to work with FP8, and they actually do those Hadamard rotations that I was talking through internally, so they can easily scale down to FP8, apply the attention at faster compute, and then scale back up. There's a lot of active work though going on here to both research and ensure this is fully supported for all targets. Weights and activations extremely supported. KV cache limited support for accuracy recovery, and then attention not great support right now. But within the next couple months, these are all going to be implemented, and fairly safe to say that they will have full accuracy recovery. Projected state. So this is my personal opinion, but 4-bit has been fairly well established as a cliff in the current literature, as well as in past deep learning domains for reasonable accuracy recovery. Yeah. So what we're going to see is whether or not FP4 actually works out. FP4 is a little bit worse of a format than INT4 actually for these distributions, but Blackwell added support for FP4. So there's a lot of work going towards creating FP4 models that are essentially FP4 across the entire model, so that they can use the native support within Blackwell for compute. And another interesting note, though, is that A100s removed INT4 support. So A100s came out before the LLM craze, and obviously, there's been some targeted research towards the LLM pieces, but A100s removed INT4 support from the V100s that had it because INT4 wasn't being used at all because they couldn't get accuracy recovery. So ultimately, 4-bit seems to be a fairly well-established cliff in the current literature.
Hey, Mark, there's another question from John.
Yeah.
And it goes, how many of the compression methods are provided in the LLM compressor library?
Yeah, let me go back to that real fast. Rounded nearest, GPTQ, smooth quant, and AWQ are all supported currently. And then there is active work going towards enabling incoherence processing methods like Caret and Quip and QuipSharp and things like that. QuipSharp is a little hard because there's codebooks. Codebooks don't really scale well for enterprise use cases, but those are in progress. And then we definitely want to expand after that quickly to the Aqua KV and Squat to see what we can do with KV cache compression. Okay, let's dive into pruning/sparsity. So looking through a review on that real fast, we're removing or inducing sparsity, so putting zeros into the network within targeted parts. And ultimately, this leads to fewer values to store. We have to compress it, though, so we do pay a compression penalty if we're storing those. But additionally, it also enables faster compute, provided the hardware supports it. And this is where we get into a little bit of a difference, which is that it's broken into unstructured, where we're just putting zeros anywhere in the network, versus something like semi-structured, which is 2.4. And this 2.4 is specific to how NVIDIA implemented their hardware for supporting sparsity. So given a block of 4 weights, starting at 0 and then indexing up, given a block of every 4 weights, only 2 of those can be 0. It can be any 2 within that, but only 2 can be 0. So ultimately, it only supports 50% sparsity, but it does have a little bit of flexibility as compared to something that's more structured. So what we can see here is the white would be 0 entries. So this is adhering to a 2.4 sparsity structure. And you can see as we're going across here, right, here's our 4. These 2 are 0, these 2 are dense. And then in the next 4, these 2 are 0, these 2 are dense. So what that means is that we can compress it so that we're only keeping the compressed values, and then we have to store the indices of where the compressed values are so we can blow that up when we need it later. The state of pruning and sparsity, not as verbose as quantization, primarily because sparsity requires a lot more on the training side to be able to converge these methods. As you notice on the quantization side, those are mostly, as I mentioned, either data-free or calibration pathways. Only like 1 or 2 did fine-tuning to get their state-of-the-art results. Sparsity, on the other hand, you pretty much have to train to recover. So notable research developments on the side, we have sparse GPT. So it utilized second-order functions to induce sparsity and update weights. This is exactly the same as GPTQ, just applied to sparse GPT. So again, treating each layer independently, we're just solving that linear function and defining a second-order method so that as we remove set weights to 0, we can update the remaining weights. And additionally, you can figure out which weights are going to affect the reconstruction error the least. Wanda simplified on top of that, and is actually really elegant and really elegant and simple setup. They're just taking the magnitude time the activation, or sorry, the weights times the activations and the magnitude of that. So again, kind of going back to what we looked at with AWQ and smooth quant and things like that, it's a very common pattern that generally gives you the most information. So all that they were doing is ranking the weights based on that. The ones that came out the smallest, they set those to 0, and they got pretty similar results to Sparse GPT. Sparse GPT was still a little bit better though. We also had scaling laws for sparsely connected foundation models. I included this one because this was a very verbose study on what does the upper bound look like for sparse models and training sparse models. And essentially they scaled very similarly to dense models. You would start out lower because these were starting as sparse from scratch. It's a whole other detail, which I'll get into in a second. But yeah, if you keep training, they will keep converging. So ultimately, it became to be able to generate these sparse models, it just became an argument of how much training can you put into it. We then had Squarehead, which introduced a unique distillation method plus sparse GPT to converge sparse models. I'll go through the distillation pieces a little bit later. But ultimately, they were using a layer-wise distillation, which formulated it as a vector rather than a probability distribution. And I'll go through that in a little bit on the differences between those. But the notable points on these is that Sparse GPT and Wanda, they could get to 50% with, most of the perplexity preserved, but the benchmarks, you'd see like a 10% accuracy drop on those, things like that. Squarehead improved significantly on that, where you were able to get pretty much full accuracy recovery at that 50% level. On the activation sparsity side, this is where we're looking at putting zeros in the activation so we can exploit those either for storage or for compute. ReLU Strikes Back was a pretty popular one where they put ReLUs into the LLMs and exploited the activation sparsity. I'll go through the results on that in a second, but overall worked out pretty well. Then we had Sparse Llama 2, which was further pre-training with sparsity. So essentially taking Squarehead and scaling that out to pre-training. And that was able to get up to 70% sparsity with full accuracy recovery. And then finally, there's a new one that came out called 2-4 proximal operators. This was exploiting local correlations to induce better sparsity mass. It's somewhat similar to Sparse GPT and what they were doing, but they were solving it in a slightly different way. But ultimately came out around the same results, which is 50% is hard without retraining. So let's look through the current research state. As I said, 50% 2-4 sparsity for semi-structured works fairly well, provided you're retraining. You can get full accuracy recovery. If you're not retraining, then you're going to see 5% or 10% generally decrease in accuracy, highly dependent on your eval set and use case, things like that. And then if you're doing retraining again, 70% for unstructured. And the big part here is that we are starting from a converged model. Then we prune, then we retrain. And the main thing here is that once the model's converged, the magnitudes and things like that pretty much correlate to the pathways, the optimization pathways that were unused as we were training the model. So it's fairly safe to remove those. Whereas if we were to remove them early on in training, then we're removing that search space for the algorithm. So essentially you fall back to what a smaller model would do. So you can get to 70% for unstructured and converge to full accuracy recovery, provided that you are retraining. For the ReLU setup, they were able to get competitive results as compared to non-ReLU and induce around 50% activation sparsity on average. It differed based on the model, but overall pretty good results. 50% is pretty good for activation sparsity and generally what we saw in other deep learning domains as well. So current production state, 2-4 sparsity support gives you about 30% better inference performance on GPUs. This is supported in VLLM, and I think it's only in VLLM, at least in terms of an enterprise solution. But yeah, that's mainly it. There technically are some CPU implementations like Deep Sparse that's no longer supported that supports unstructured sparsity for LLMs, but CPUs are fairly slow for execution for these. And then projected state, I broke this into two different pieces for my opinion. 85 to 90% sparsity definitely would be achievable, but it would take significant compute. To put this in perspective, in the past, we were able to get to about 95% sparsity. Actually, I think even 97% sparsity on ResNet 50 in the image on the computer vision domain, but that was with training for about 2x the original training time. So these would be achievable, but it's a significant amount of training to do it. 70% is likely to remain the standard and the highest level without a significant investment in compute. All right, we're running low on time, so I'm going to try and go fast. Structured pruning, low rank, and weight sharing. So on the structured pruning side, as we said, remove entire channels or layers from the model. Just going back real fast to give an example of what that is. Rather than inducing sparsity in here, we're going to cut off whole columns or rows or even this layer entirely to be able to reduce the impact on how much compute we need to run and memory. Oh, sorry, I skipped past that. There we go. All right, low rank factorization. This is where we're taking that large matrix and we're trying to approximate it's a standard thing like you would do a singular value decomposition and things like that, where we're taking the matrix and trying to break it down into two smaller matrices that are easy to run, but with that you're necessarily getting rid of information. But you are able to save on compute and memory. And then weight sharing, this is where we force multiple layers to share the same underlying weights. Works really well for the total size of the model, but doesn't save anything for compute or memory bandwidth. Notable research developments on this side, low rank decomposition LLMs, not great. The most recent one that I know of was able to get 9% compression, so really not comparable to the other sides on quantization, sparsity, and others. Nematron is a fairly established setup that did a significant architecture search and structured pruning, like channel pruning, things like that, which resulted in much faster training. There's also SWSC, which did weight sharing for similar channels and LLMs. There's some notable pieces inside of that. But current research state, 9% compression low rank, about 20% structured. And then current production state, there isn't much support for low rank, but since structured is just changing the dimensionality of the model, that is fully supported across various platforms and engines. Projected straight, low rank is likely not to really go anywhere. I think quantization, sparsity, and things like that are much more promising, and that's primarily because they can. Whenever you're doing the low rank decomposition, you're making assumptions about reconstruction and things like that, which generally, if you're doing just a linear layer on its own would work well, but because we have multiple layers chained together, there's not really a way to update for that error and it doesn't work too well. And then generally 40% is shown to be the upper bound on structured techniques. Again, that's going to be with a lot of compute based on other domains like computer vision and NLP. All right, got a little bit of time left, so we're going to run through these really fast. Extend the model, speculative decoding. There we go. Okay. So we have draft methods. There were a few papers that came out on this. This is where we take a smaller model as our speculator, and we use that to predict multiple tokens ahead, given the current state of the model. And then we use a larger model to validate. Those usually gave around 1.5x speed up 2x, somewhere around there. Then there were a series of Eagle, Medusa, Haas, and Eagle 3. These are, for the most part, state of the art right now. And these focused on adapting the architecture. So you could add a few layers on the end of it. You essentially would keep the classification head that you had, and then you would pull from either one spot, the output embedding, or sorry, the latent space, output latent space of the model, and then run that through a transformer layer or a linear layer, things like that. Or you might pull from multiple spots within that larger model. And ultimately what you're doing is training a much smaller model, usually just a single transformer layer stacked with a linear layer or something like that. This is what Eagle series did and Haas. Training those to converge and try and predict several tokens ahead. The extra pieces on top with Eagle 2 and Eagle 3, things like that, those got into complicated ways of token prediction, where they're actually predicting a number of different tokens and creating a large tree of possible pathways that it could predict. This way you can get essentially conditional probabilities that you could better filter out and say what the next token should be after you map out that tree. So I'll go through the results in a second. And then Haas essentially just expanded out the training to converge that smaller speculator much better. So current research state, generally somewhere around, actually 3 to 4x is probably a little high, usually more along the lines of 2 to 3x, but with up to around 4 accepted tokens. So that means that you're able to predict 4 tokens ahead, and your larger model agreed with that distribution. And then current production state. So support for Eagle 3 and other methods are slowly rolling out. This is an active area of engineering right now. And there's some new repos spinning up that we're actually working on that we're really excited about, and hope to be able to push out to a larger community very soon. Projected state, 5 tokens seems to be a current bound based on, in terms of being able to predict out. May be able to double it with with a little bit more complicated of an architecture, as well as some significant training investments. The other thing to note on speculative decoding is it is highly dependent on that training set that you use, that correlating with your usage set, right? So if you didn't train on coding at all to create that speculator, it's not going to predict well for coding tasks. All right, let's run through real fast. Type 3, teach a smaller model. Knowledge distillation, it's a few different things on here. Output distillation is the main one, where we are just looking at the output distribution, essentially the classification coming out of that classification head for the teacher and a student model. And you're using the teacher's probability distribution that it output to teach that smaller model. And that's essentially giving much more information to that student model than it would get training on its own, because now you're getting conditional probabilities and more minor probabilities and things like that for tokens that are similar and things along those lines. Vector layer-wise distillation. So layer-wise distillation came out where you're just taking layer to layer and matching on the output distribution. There was some earlier research on this that was treating it as a probability distribution, which did not work out really well. But what did is treating it as a vector distribution, where essentially you can just define it as the mean squared error and minimize that loss between multiple points, multiple hidden states within the network of your teacher and your student. It does require that those are the same size, but there's also some research towards being able to add a projection layer so you can take that larger model and project it to that smaller space. And then probably the most popular right now is DeepSeek. They have a number of distilled models that they use output distillation on, and work fairly well. Current research state, if you have a targeted task, usually you can get up to 10x compression just by doing some distillation, but usually around 2x in terms of improvements in inference for general. And then current production state, this is fully supported since we aren't changing the model at all. This is all on the training side. And projected state, the current research state seems to be about the limit. You know, we might change from these numbers a little bit, but generally these are going to scale as better training methods come out. We'll see improvements in pre-training and post-training, and those will scale with knowledge distillation as well. Data distillation, there's obviously been a lot of talks of random samples about this, so I'm not going to go through these too much. But active research area, including Instruct Lab, with being able to create much smaller models, but with targeted data and be able to expand synthetic data and things like that. You can get on the order of 10x smaller models, outperforming the larger models. And production state, again, full support, since we're just looking at the models and similar to knowledge distillation. Before I go through the conclusion, one thing that I didn't get in here that I did want to talk through is just compounding all these together. That is an active research area where we can take sparsity plus speculative decoding plus quantization and knowledge distillation, things like that, to all work together. Those have putting all those together has a really, really large upside, probably on the order of 10 to 20x improvements in performance at the extreme end if you compare all those together. So just want to call that out. But otherwise, wrapping up, LLMs are powerful. Deployment costs scale faster than model size. Compression is not optional. It's essential for scaling, and you can essentially get a lot of savings for free. All these techniques offer some real-world trade-offs that can make it a lot cheaper to deploy. And research is moving fast. Production readiness is still lagging, but that's an active area that we're trying to get caught up on and make sure that production is matching. 8-bit and 4-bit are your best bets for going to production right now. And yeah, I think that's about it. So thank you, everyone. And I guess we have 1 minute for questions. I apologize on that.
Yeah, we'll take a couple of quick questions. Maybe, Mark, maybe we should first thank our speaker. And so this one is from Rodri on what would you say it would be the best way to test for quality loss, running relevant benchmark to whatever the production use is going to be, for example.
This is a very, very interesting topic. We actually have a paper out called "Give Me BF16" or "Give Me Death," essentially a rebuttal paper to a very popular tweet that went out. It is saying that quantized models couldn't match the 16-bit models, and the interesting part there is that they can, but you definitely need a lot of tuning, and as you brought up, you need to ensure that that you're evaluating on the right sets. Academic benchmarks are a good correlation towards this. So if you're using LM eval, the Open LM leaderboard V1 and V2, those are generally pretty good correlation to how your usage is going to be. But I definitely recommend creating a dedicated eval suite for whatever you're deploying to. If you're looking for something and you don't have that data available, Arena Hard is really good on the chat and instruction following sets. Human eval is really good for correlation on the coding side. And then I forget the summarization evals, but there's a few on summarization that really help out a lot with RAG and things like that.
Oh, maybe like one more, because we're a little out of time. But so William asked, when applying these sparsity techniques, does the end result could be interpreted as an MOE?
This is a very, very interesting question. Somewhat yes, somewhat no. MOEs are definitely a form of structured sparsity. The interesting part on the MOEs, though, is that they do have a routing layer. And that routing layer is what makes it a little bit different from traditional sparsity techniques. So you're routing, you're able to decide what portion of the network to go to. So you're keeping the dense state of all of those, and you're still actively training the dense state of all those. So they do preserve, a little bit. But yeah, so that's the primary difference, whereas in sparsity, we're not routing to different portions and we are removing information. The point to kind of add on to those is that these should be, I haven't seen any research towards it, but these should be very orthogonal to each other. We're actually for all those mixture of expert heads, the experts within the MOEs, you should be able to prune those, at least if you're able to retrain to, that 50% target each individually.
And then there is another question on the data distillation. So can you elaborate more on data distillation?
Yeah, a little bit. I think Akash, you're definitely more positioned towards that. But yeah, I mean, for the data distillation, primarily just looking at essentially, whenever you're training models, usually you have a lack of data overall, or you have a lack of high quality data. And whenever you're pre-training an LLM, for example, you're training over a large corpus of text that has a lot of irrelevant data in it. So by using a larger teacher model, you can essentially focus the data distribution that you're training on to match what you care about in terms of evals. And so you can get a lot more efficient data representation, so you don't have to train anywhere near as long. And you can also, because you don't have the noise coming in from that, you can converge higher in accuracy. But Akash, I'd defer to you if you want to add on to that.
Yeah, I think because we're out of time, if there's an interest on this topic, as it seems, we can cover this in the next session. we've unfortunately run out of time a little bit. So I do wanna take the time to thank Mark for an amazing presentation. It's very comprehensive. Another probably. Awesome. So the recording is going to be available in some time. But again, thanks a lot for everybody on the call, as well as people who tuned in to YouTube. And once again, thanks, Mark. This was awesome.
Yep. Thank you, everyone.